My name is Adrian. I'm the director of GITIA research group in Tucumán, Argentina. What I will be presenting today is joint work with CIPROSA. CIPROSA is the Sistema Provincial de Salud, is part of the health department from the province of Tucumán. So, and it's an ongoing project. The artificial intelligence I will be presenting is complete and tested. We are working in the next version, and simulations I will be presenting. Some are complete, we are working on it, and the real tests are just in the planning stage. So what's the problem we're trying to solve? Do you have electricity right when and where you need it in your hospitals? Extreme weather conditions are increasingly common globally. There was a very large problem in Texas in February 2021. We have had serious heat waves here. So, and those come many times with long days, outage for everyone, large homes. And during the pandemic, we had the problem, many people had the problem that you had to turn intermediate wards or rooms into ICUs, intensive care units. So the problem is that you need to protect energy in any outlet in the building. You cannot limit yourself to have you need to take your patient to the ICU in order to be able to have energy during an outage. People is going to die. Do you have a proper control and monitoring system over the grid? So what we're proposing is an autonomous virtual emergency grid for future generation hospitals. That is, you use your original complete grid of the hospital and mount over it a smart virtual grid that mounts over the ordinary grid. That means each and every outlet in the building will know what to do, will know how much energy you have, and how the devices connected are important or not, which is the priority. So if the outlet is in an operating room, it will provide energy, but if the device is in a TV set, in the waiting room, it will deny it. And the system adapts the consumption to the situation and to the generator limit. If the limits of the generator change because, for example, one of the two generators stops, the whole building will know what to do and adapt itself to the situation. So that's the main idea. What's the law? Hospitals are obligated by law to have generators. All the hospitals even in this country have generators. The emergency grid is in all cases physical and covers predetermined zones designed in the design stage and construction stage of the hospital. Generators are a complex technology that needs to be carefully maintained and constantly checked. Let's say every weekend needs to be checked. Operating rooms must have UPS, that means uninterruptible power systems. The surgeon does not need to know what happened if there was a problem with the line. Not always the case. And ICUs require special air conditioning with high efficiency particle air filters. What's the reality? The reality is that generators are very expensive and labor intensive to maintain. It is not true that all hospitals around the world have the capability, the administrative capability, the money and the personnel to make that kind of maintenance. Sometimes generators are 40 years old or more. They work, they function, but the labor-intensive maintenance is not always properly done. And even if you are in a large hospital with proper administration, with personnel, and with money to perform a proper maintenance, you have problems like water leakages in the diesel that are very difficult to diagnose. If it was a large rain, the water is going to go into the diesel and the generator is going to stop in the middle of the outage. And the pandemic forced many hospitals to turn intermediate wards into ICUs. So you can get a special air conditioning, even if in a tank, you can attach a new air conditioner with a HEPA filter. You can put a second generator in order to make sure you don't lack power, but updating the physical emergency grid is almost impossible. You need to vacate half the hospital for months at a time, and in an overwhelming situation like we are all living today in many parts of the world, it's completely out of the question. And flexibility in the emergency grid is critical. You cannot assume that you will only have monitored patients with life support in the ICU. You will need to put patients with monitors and with pumps and with different equipments, life support equipment, all around the hospital. So you need your emergency grid to be flexible. So what do we propose? We propose a distributed control of the electrical grid. The main point to control is the air conditioning. The air conditioners, as far as we have been able to gather information here from hospitals, from the health department, from Ciprosa, and from the literature, there was a report from the UN about it. The ACs, the air conditioners, are the main consumers. So controlling the ACs is the main part of the problem. And sequentially start the ACs is a critical point. After a 2 or 3 hour blackout where the hospital didn't have energy, it has happened and it will happen again. The hospital is hot, all the rooms are hot, so whenever your generator starts and you get power, all the generators start at the same time and you get an outage again because the generator gets overwhelmed by the request of energy. So sequentially start the air conditioners in order to be able to not overcharge the generator. It's a critical point that the health department is asking from us. Also, you need to know each and every air conditioner, each X-ray machine, and each device in the hospital, exactly where it's connected. So you need to automatically detect the topology of the grid, where everything is connected, which phases are where, and what are the lines, and how much is the charge in any line. That is a variation of the previous work we done with phase identification, and we are working on it. It should be easy to install because vacating the hospital, as I said, is completely out of question, and you need to make it explainable. You cannot pretend a doctor to use things he does not understand. He is responsible for the life of his patients, and so is the hospital. So they tend not to trust technologies they do not understand, and I happen to agree. So we are proposing an explainable artificial intelligence. No black boxes, like, for example, neural network. So how do we accomplish that? What's the virtual emergency grid? The virtual emergency grid means use the ordinary physical grid. By definition, the emergency grid, physical emergency grid, reaches only part of the hospital. And you need to be able to use any outlet in the building. So you need to mount yourself over the ordinary physical grid and connect your generator to the physical grid. And we change the outlets. We take out every outlet in the building and put a smart outlet that contains a 32-bit microchip, it's a very small microchip, and a communication unit that receives a broadcast from the generator. The only information you need to get in every air conditioner and every device is the consumption in the generator and the timestamp. And with that information, every device knows what to do. It's a distributed intelligence. So each and every device in each and every outlet determines if there is enough energy and if your request is priority enough to grant your access to energy, and if it will cause an outage if For example, if your air conditioner is too large, you cannot give you access because it will produce an outage. And the main challenge was to do it only with broadcast. You need to keep into account, considering that hospitals, main hospitals are usually large, 3 or 4 buildings distributed around the block, and with 1 or 2 generators that need to work in set. So making a smart SCADA-like system is completely out of the question for complexity and for installation and for many reasons. Money and expense is one of the reasons. So making it only broadcasting only small information, as I said, is only the timestamp and the number saying the consumption of the generator in the moment, makes it for a very small message and a very simple system to install. So the virtual emergency grid is another layer of abstraction working over the physical grid, ordinary physical grid, that allows the system to decide where the energy will be used. It's a flexible, cheap, and easy to install system. As to how we do it, this is an artificial immune system. This is the heart of the system. The affinity is an equation, it's a distance, many distance can be used. It's a differential equation if you see, because you have the derivative here, and this is the squash that gets the original function. So you have a set of differential equations. This is a single function that's related to the decisions you have to make to where the energy is enough and where, if your device can be authorized to enter, or it will overload the system. So it's explainable because it's a set of equations. You don't have training, you don't have coefficients that you don't know what to do. Each coefficient plays a part and has an influence, and you have margins of security that can be adjusted, and you can adjust the response, and the system do not present unexpected behavior. I cannot get into the details of the real equation because the patent is not filed yet. So this is a simulation over one of the largest hospitals in our city, in our province, Central Salud Senor Santillán. It's a very large hospital with 2 generators providing 380 kVA total. And for security reasons, and according to the manufacturer, you need to set your limit at 85% of the maximum nominal power. If you go above 90%, you get your energy to flicker, you get your main phase overwhelmed, and you can have an outage if you go over 90 and 95. Experience also shows that if you do it, you will really get an outage, and the generator will go offline. So this is a Gantt diagram. This is minutes and air conditioners. These are the 2 main larger air conditioners. Those are rooftop air conditioners with over 30 tons of refrigerated power that provides refrigerated clean air to the main ICUs. You have 19 other large rooftop air conditioners to provide air for other rooms with patients, not ICUs, but large rooms. And you have many splits, almost 120 splits across the building, refrigerating important rooms. And you see the black parts are stops, the white parts are starts. And you see there are only short stops, 3 to 5 minutes, and distributed along the 30 minutes in this case. And we achieve the blue line. The red line is 85%, the black one is 100%. And as you can see, the air conditioners start in a sequential fashion, so you don't overwhelm the generator and make sure you don't have an outage. That's the main problem. The air conditioners going all at once and provoking an outage. This is the main solution. We get the air conditioners to start sequentially and respect the 85% limit, so you make sure everything goes to plan. And these are the progress from 2017, where we introduced the first version of the intelligence. The top one is the 2017 version. This is the today version. And you have 3-minute stops and 5-minute stops have reduced now to only 3-minute stops. Every device stops only for 3 minutes, a couple of more longer, but no 4 minutes or even 4, only one. This is the number of air conditioners. You have 144 air conditioners. You have total time stop in the hour. And you see in 2017 we had many air conditioners that didn't stop and many to stop over 15 minutes up to 22 minutes. This is a histogram of the same diagram, and here you see the same information. But some 10 to 12 air conditioners didn't stop in the hour, and there were some air conditioners with bad luck that started up to 10 to 2 minutes. And we got that to a very fair, everyone stops 9 minutes in the hour up to 12 minutes in the hour, and you can see the difference in the picture. The challenge is to get this picture, is to get this result, is to get everyone to stop more or less 10 minutes, 10 minutes plus or minus 3, without communication. That it's very easy to do this if you centralize your communication and you do a SCADA-like system. But doing this without centralized communication, without talking to a central that makes a decision, or talking to your neighbors in order to know what to do, is a challenge. And we have been able to use the artificial immune system in order to do that in a completely explainable way and trustable way. This is a simulation. We have performed the simulation several times, and the results are practically the same. So it's stable, it's trustable, and every stop has a reason, and you can touch coefficients and observe how the results change. So this is the system we have developed. It's a cheap, distributed, easy to install, explainable, and dependable system for the emergency brake control. It's distributed because there is no way to install, at least in Tucumán, for the budgets we have and for the large buildings there are. It's completely impossible to install a SCADA-like system. So it must be easy to install, and changing the outlets and making a virtual grid achieves that. It targets the physical emergency grid, meaning you cannot change it. It's impossible to take it out or modify it. So we developed a virtual grid that allows you to use any outlet in the building according to your priority and needs. Always a doctor, a medical professional makes the final decision about the priority, but the system respects that according to its possibilities. But the energy, as you saw, is distributed evenly and fairly, and according to the possibilities and according to the priority. Our simulations show that the system provides a practical and affordable solution. You don't need to control everything in the hospital to make it work. You only need to control your air conditioners and some other main consumers. So it's even more affordable than what I said. You don't need to change all the outlets but some. And it's very practical because it solves all the main problems that we have been asked by CIPROS. So it's also useful for renewable energy. One of the main problems at the time of using renewable energy is to respect the maximum and system hazard. And the problem can also arise in developed countries with high-budget hospitals. Even if you have a lot of money and your own personnel for the maintenance, water leakage, among other problems, can go undetected, and your generator can stop in the middle of outage. And even in developed countries, you are having weather-related outages that last long days, and it can happen all around the world. It's an international problem, and we hope to contribute to the system to make it better. Thank you very much. Look here. Please. Oh, what a great question. The the update, the time of the frequency of the update of the messages. If the messages start to get low and you get latency in your messages, the system gets problem. But we have tested it with 30 seconds or more, and 200 milliseconds is standard. But you can get up to 30 seconds delay, and the system still works. And more than that, it starts showing problems. And yes, over a minute, you have serious issues. That's the main parameter. I like your questions. Yes, that's called the safe mode. We are working on predicting, given the time. I mean, if it's in night in the middle of winter, you are surely not having a problem. And if it's December 25 here, the summer, and you have had 2 or 3 days of intense heat, so even if your central is not giving you the information, you can assume that there are problems. So that's what we call the safe mode. And to make the system resilient to communication failure, we are trying to work on that. Good question. Thank you.